All right, so the second assignment is probably released now, and it's a short assignment. It has a lot of steps, right? But it's fairly straightforward. There is a base code that I've given you, and okay. So this will look very similar to the first one, right? So there's some skeleton code, and all you need to do is sort of fill up these functions, and in the assignment description it tells what each of these functions do. Please don't change the structure of the functions in terms of their inputs and outputs. They need to follow exactly what is here, right? Because the TAs are going to take your functions and then run them independently in their own code. So if you change it, then they won't know that you changed it, and you'd get points deducted, right? So this is fairly standard assignment, but it is very interesting. So I want you to sort of get started on it. You'll find it fairly interesting. Okay, so there are two parts here. One of the parts is about the Gaussian discriminators that we talked about just a class before the midterm. So you need to implement two types of learning algorithms. One is called LDA, or linear discriminant analysis, and the other is called quadratic discriminant analysis. They're both sort of variants of the same idea. Okay, so if you refer to these slides, you'll see what I mean. All right, and so there are two things you need to do. You need to train it on some data that I have given you. It's two-dimensional data, and then you have to test it and sort of tell us what your accuracies are. And then you also have to plot the discriminating boundary. Okay, so this is something new that we have not really talked about. But if you look at the base code, you don't really have to write the code for plotting. So the code for plotting is already here. Okay, all you need to do is implement your testing functions, and if they are correct, then the boundaries will be correct. Okay. Now, but this is a very interesting concept which you would find useful in other places as well. So the idea is, how do you plot a boundary, right? So if I give you a classifier, how do you plot the boundary where it makes the discrimination? So in the past we have looked at linear classifiers like a perceptron, right? So there it was easy to do. So if I had given you a training data set where you had some positive points and then some negative points, right? And you run your perceptron classifier, and then you get a line, right? Because perceptron gives you a line W. That's easy to plot because it's geometric, right? So you can plot the line with this equation, and it would come to something, whatever it learns, right? So that's easy to do. But what happens if you want to plot a non-linear boundary, like a boundary that is created by a neural network, right? Then because there is no geometric equation, it's hard to plot that, right? So in that case, what we typically do is we take our input space like this, right? And then we divide it into cells. Typically we call it a mesh grid. So in both dimensions, we divide it into this grid. Okay? And then each point at each vertex is a point, is a training data, or is a test point, and then you test your classifier on each of these points. Okay? So what happens is that you test your classifier. So each of these point is basically a test point, x1, x2. If this is x1, this is x2, right? So what you do is, when you test your classifier on each point and you put that classification label back here, you can then view it as an image, right? So for example, if your classifier is predicting +1 and -1, what you would do is you will put a -1 on this grid wherever it is -1. I mean, it will be structured just like this, right? And then somewhere it will be +1, right? And then if you just sort of color it according to the color, so if you give red color to the +1s and green color to the -1s, then you can see at some point there is a boundary, right? So that is how we plot non-linear boundaries. So for example, in your neural network case, right, instead of looking at digit data, if you had trained a neural network to classify this kind of data, right? You would have learned a classifier, right, a neural network, and then you could have drawn the boundary by sort of doing this mesh grid business, right? And that way you would have seen that neural networks tend to learn a complicated nonlinear boundary, all right? But you will see it firsthand when you do this when you do this assignment. So don't just use this as a black box tool to plot your answer. Do look into it and see what is going on. So if you look at it, all it does is it creates a mesh. If you see, in fact, that function is called mesh grid. So what this function does is it just basically not samples, but divides your space. Here I'm assuming that your space goes from -5 to 20, and it divides the space, and then it sort of finds the classification label at each one of those points, and then it assigns some colors to them. So here if you see, I use a scatter function, and the color is basically the label, and then when you see it, you would be able to visually see the boundary. Any questions with that? All right, so this is, so I'm quickly going to go through the rest of the assignment. So this is the first part. Then the problems from 2 to 6 are more about regression, which we will do from today onwards. All right, so you need to sort of go through these and basically work these out. In each one of them, you have to write some code, little bit. You have to analyze some data that I'll give you, which is also attached. It's a diabetes data set. And then you will have to sort of prepare a report where you have to report some things like, okay, why do you think this is better? Why do you think it is not? All right. So make sure that you spend some time on the report as well. What you will see here is that the data is minuscule compared to the neural network data set, so only 242 data points. So this will run really fast. So you don't have to worry about running it on Timberlake or Metallica or anything. All right. Okay. Any other questions? This is due on April 6th. Okay. Okay. So let's start with our discussion. So last time we stopped at neural networks. No, this is not good. Last time, also not neural networks. Last time we stopped at linear regression, or at least we got started with linear regression when we had an alarm. All right. So the basic idea was easy, right? The job of linear regression is to predict a value instead of a label given some input data. So X is your input data and Y is the target that you're trying to predict. And the learning task is, because in linear regression you assume that Y and X are connected through a linear function, which is W transpose X. So your job is to learn that function or those weights given some training data. All right. So as I told last time, typically we assume that our data is arranged in a matrix. We call it an input matrix, and that's denoted as an X. And the labels are arranged in a vector, which is called our Y, which is target vector. Okay. And then I also talked about including the bias term, right? Because we need the bias so that our line doesn't have to go through origin, right? So we add that by adding a 1 at the end, right? Then we looked at two interpretations of linear regression. One is, of course, a standard fitting the line example, where the job is to learn a line which passes through your points, right? Of course, you won't do a perfect job, because unless the lines are in a line, unless the points are in a line, right? So in principle, if you have 2 points, you can draw a line. So it won't ever happen that all your points are in a line, which means that you would have to do a close enough job, right? So this is another example of the case where your inductive bias, your hypothesis is not exact, right? So you're assuming that all your data is on a line, but it's not really, right? So that's where you introduce some error. You say, okay, it's okay if it's not in a line. I'll allow for some error about the line, and then I want to find the line such that the error is minimized, right? So that's sort of the basic idea. Then today we are going to look at how do we estimate these parameters, this W and this sigma square, right? And there are many ways to do that, and what we will see is that all of them sort of give the same result, but we still would like to go through the process of all of them, because in future when you write new, algorithms for other type of regression or classification, you will see the same math being useful. Okay, any questions so far? Okay, all right. So the first way to do to learn the parameters is the MLE approach, maximum likelihood estimation, right? The way this works is that since if you remember, we assume that our if you remember, what we assumed was that y, in a probabilistic interpretation, that your target y is a normally distributed or a Gaussian distribution with mean at W transpose X, okay, and some variance sigma square, right? So this is slightly different from probabilistic the probabilistic classifiers that we have seen earlier, where we assume that our y and x are both random variables, right? For example, in LDA and QDA that you will do for your assignment. But here you're not really assuming that x is a random variable, okay? All you're saying is your y is a random variable, but the way it is connected to x is through this function, right? So now you need to estimate this w, okay? So the way to do it is to find a w which maximizes the likelihood of y, right? Because that's how the maximum likelihood estimate works, right? So what is the likelihood of y? So y is a vector here, right? So we are going to assume that y is a vector which is basically all the training labels or training target values arranged. So let's say there are total n target values, right? So then we can say that the likelihood of this data set, which is a function of w, right, will be equal to product of the probability of each y, I equal to 1 through n, right? That's the likelihood equation. We are assuming that each of these are independent, right? So that's an important assumption which we often make without even thinking about it, but this is a very key assumption. Without this, it won't be possible to write, right? So if somebody tells you that, you know, you can't assume that your outputs are not related to each other, then you can't use it, right? So for example, oftentimes what happens is people do this spatial regression where your data points are arranged on a space, right, in a sort of like on a map, right? So in that case, the value at one location of course depends on value around you, right? So then using regression won't work, right? So that's where people use spatial regression, which is a different area itself, okay? So here we are assuming they're all independent, so which means you can write it like this. Now what is each one of these? And then you can also compute the log likelihood, which is basically taking a log of this. So the benefit of that is that then it becomes a log of summation instead of a product, right? Now what is this? This is because we are assuming that your each y, actually I should write yi, right? So each yi is a normally distributed random variable. Then this can be written as I equal to 1 through n log of 1 over under root 2 pi sigma, right, and exp minus half sigma square yi minus w transpose xi square, right? This is the standard equation for a normal distribution. If I take the log, then this thing becomes like a sum of these two quantities, so it becomes summation I equal to 1 through n. Then I'm going to write this because this is 1 over, so it will become minus, right? So minus log of 2 pi and half because of the square root, and minus log sigma, right, plus, or actually minus, and then log of exp cancels each other out, so it's 1 over 2 sigma square yi minus w transpose xi square. Okay, then now what we need to do is we need to find the w that maximizes this log likelihood. So we need to take the derivative of this with respect to w, right? So we need to do d by dw of log of L. Okay, now what you can see is that this portion, now we are going to do two derivatives. first we are going to find the W, and then we are going to find the sigma square. So when we are finding W, we are going to assume sigma square is constant, but because that doesn't depend on W. So then what will happen is these terms will go away because these are constant. So all you would be left with is minus 1 by 2 sigma square d by dw of summation yi minus w transpose xi whole square. Okay. Now there are many ways to solve this, but I'm going to use one way, which is going to be easier to do. So now let's look at this quantity over here. Okay, this is I equal to 1 through n yi minus w transpose xi square, right? This can be written as, if y is the like a vector which contains all of these quantities, this can be written as y minus xw transpose y minus xw. So X is your input matrix. Excuse me. X is your input matrix and Y is your target vector. Okay? And I'm guessing a lot of you would have used this in your programming assignment 1 as well, because if you remember, this looks very much like our error, right? The squared error. And to do it in instead of, if you want to avoid the for loop, all you do is you compute error in each as a vector, and then you do a dot product, right? So if you work this out, you can see why it is equal to this. Any questions about this one? Right, so this is fairly easy. So what I'll do is I'll use this result here to make it look a little more manageable. So so minus 1 by 2 sigma squared d by dw of y minus xw transpose y minus xw. All right, and then there are many ways to solve this this thing. One way to do it is you can just say 1 minus 2 sigma squared. You can open this, transpose goes inside if it's a summation or a thing, and then you can multiply them, and what you would get is y transpose y plus xw transpose xw, right, minus y transpose xw minus xw transpose y. All right. One thing you can see is that this, right, this value is what? So if you look at y transpose xw, right, so y is n cross 1 vector, right, so which means that y transpose is 1 cross t, 1 cross n, x is n cross d, and w is d cross 1, right? So if you multiply it, it's a number, right? It's a scalar value, which means that this and this would be the same, right? Because this is essentially a transpose of this. So which means, and because a transpose of a scalar is the same value, so both of them are actually the same thing, right? So this is just a simple matrix tricks that we're going to use to make our life a little easier, all right? So now we can write it as minus half sigma square y transpose y plus, and you can rearrange this as well, so this becomes w transpose xt xw minus, and then you can write it as 2 times y transpose xw, because this and this are the same, all right? Oh, sorry, I forgot the d by dw. Right. So now you can bring the derivative inside. This term will go away because this doesn't depend on w at all. So it's going to be minus 2 sigma square. This is 0 plus. Now this is where you might want to use the matrix cookbook. But if you look at the matrix cookbook, the answer for this, if you want to do a derivative, so d by dx of of x transpose ax, right? That's a standard result in the cookbook that's given as 2 transpose XA. Okay? That's if you look, I mean, you can actually derive it, but you know, why do you want to do that when you have the cookbook, right? So so I'm going to use that result here. So this becomes 2 times W transpose XTX. In this case, A is XTX, right? Minus, and this is just because the W is just outside, so this is just going to be 2YTX. All right, any questions so far? All right, this is fairly standard matrix algebra. Then we set it to 0. So setting your derivative to 0. So then when we set it to 0, this doesn't matter. Then all you need to do is 2W3 XTX is equal to 2YTX, right? XX go away. What happened? What? Oh, okay. Yeah, that's good. And then I'm going to take transpose on both sides because I want to get W here, right? So when I open this, it becomes XTX transpose W equal to X transpose Y, right? Because that's how the transpose works. Another thing you can look at is that this quantity, right? So XTX will be what? It's a symmetric matrix, right? This is going to be D cross D matrix, right? So XTX will actually be equal to XX transpose. Oh no, what am I saying? No, that's fine. I'm going to just open it, right? So when I bring it in, it will still be XTX. Sorry. Right? Now, to find W, what I do is I bring that over here. So this becomes W is equal to XTX inverse XTY. All right? So that's just sort of a little bit of matrix algebra, but this is a fairly standard result that you might have seen earlier as well. All right. So in the same way, you can also derive the sigma by maximizing this. That can be your homework, or you can actually look at the handouts. If you just maximize the log likelihood with respect to sigma, then you can compute the optimal sigma as well. All right? Any questions so far? So this is how you would do the derivation of you estimate the parameters for your weight and the error covariance using this. Okay, so this is what we derived, and this is what you will get for sigma as well. It's fairly standard. All right. Now let us try to do the same thing with the least squares approach. So in this, we were trying to maximize the likelihood of your data, right? Now another approach is that comes from the geometric interpretation. So remember, in the geometric interpretation, what you do is, I'm going to give you an example in 2D case, because I mean actually 1D case, and that's all I can draw. But let's say this was your X, just one dimensional, this is your Y, right? So if you remember, in the geometric case, our job was to fit a line, right? Now which line should we fit, right? Because there can be any type of line. So the line that we want to fit should be such that the error means how far each point is, should be minimized, the total error, right? Which means that this distance plus this plus this plus this plus this plus this should be minimized, right? So in that case, you can write an error function, which will be, so the error will be what? Error will be whatever your true value is, which is this quantity, minus what you predict, which will be W transpose XI, right? So of course we only want to take the magnitude, so we put a square here, and then we just try to sum it up for all data. So this is your error, right? And now all you want to do is minimize this error, right? What you will see quickly is that this looks exactly like what we were doing here when we were maximizing our likelihood. The same expression comes here. That if you think about what I mentioned earlier about the Gaussian distribution giving you the Mahalanobis distance, right? So they have the same notion. The Euclidean distance and Gaussian distribution have very transferable ideas. So that's why even if you try to compute this error and minimize it, you will get the same answer, because here it is a negative number, right? So here you were trying to maximize this quantity, right? Which means that if I remove this negative, then it means you're trying to minimize this quantity, right? And here also you're trying to minimize this. So the answer will be exactly the same. The answer, the W, will still be the same. X transpose X inverse X transpose Y. Okay, so I won't derive it because that's basically doing the same thing again. Any questions so far? Yes.
How do we know that X transpose X is invertible? Does that come from the data?
That's a very good question. So the question is, what if X transpose X is not invertible, right? Because here we are assuming, here we are saying we are going to compute this. And the answer is, it might not. And then you would run into trouble, right? And it might happen if sometimes if you have very correlated attributes, then it might happen. I'm trying to see if it would always, yeah, it could happen. It could become sort of ill-conditioned, and you might start running into trouble. So when that happens, what you need to do is you would have to change your data in some way to improve that. So there's no answer to that. In fact, the next thing that I'm going to talk about actually solves that a little bit. So here we are. So now how do you compute this, right? I've written this equation, right? But how would you do that? So you can use something like np.linalg.inv, which is basically just doing a straightforward inversion. But any applied mathematician would tell you not to do this because it's sort of not very stable. So another way you can do it is you can do np.linalg.solve of X transpose X, X transpose Y. Because think of this is a vector, right? This is a d cross 1 vector, right? So basically what you need to compute is some A inverse Y, which is just solving a system of equation, right? So if you have some system of equation Ax equal to Y and you want to find X, then you typically do a solve, right? And oftentimes solves are a little more stable than inversion, right? So you can do that as well. But that would still run into trouble if your matrix is not is ill conditioned, right? So that's the idea. So the third one is to sort of address issues like those is you can use something like gradient descent, right? Because if you look at this, right, this looks like this looks almost like what we did for neural network or perceptron, right? All you need to do is you have some objective function and you want to, and it looks convex because there's a square here, and you want to find the optimal values of W that maximizes it. So you can also use gradient descent, right? In the case of gradient descent, what you would do is you would take your JW and then you would compute d by dW of JW. You would not set it to 0. All you would do is you do new W is old 1 plus some eta times. Is going to be minus or plus? You're minimizing, right? So you go in the negative direction of your gradient, right? So you can do that as well. In fact, when you look at your assignment, that's exactly what I want you to do. I want you to try both of the options. So the first one is that you want to directly solve this in learned ridge regression, and the second one is you want to implement it using gradient descent, and then you will see what is the difference and what is the similarity. All right? Okay, so the gradient descent also would work in the same way. Now, why do we want to do gradient descent? Reason number one is sometimes if you do a direct solve or a direct inversion, the matrix might be ill-conditioned, which might lead you to some numerical errors. And the second one is that sometimes this matrix could be too big, right? So this is what? D cross D. Now, D is the number of dimensions that you have. So if you're working with millions of dimensions, right? So in areas like biology or bioinformatics, sometimes the data has very large dimensionality. So in those cases, doing this solve might be very expensive, right? So to handle that, we want to do gradient descent. That will be more, what should I say, more efficient. Any questions so far? All right. Good. So far we have looked at linear regression, right? So we have looked at different interpretations of linear regression. It's a very standard model. We have seen different ways of computing or estimating the parameters. So we have looked at the training and the thing. Now what we're going to look at are issues with regression, right? So to look at issues with regression, I'm going to turn to this this workbook, okay? By the way, linear regression is very easy to implement, right? In fact, you would be doing that in your assignment. But if you look at sklearn library, it has linear regression built into it. In fact, any statistical package, the first function you would see is linear regression, right? So I'm going to show some demonstrations here. So let's say we have some data, right? Here we are, just for the sake of illustration, I'm going to say that my data has only one dimension, x, okay? And this is my target, right? Now I have generated this data, right? So the way I have generated this data is actually by taking a line, w, and then getting some y, and then adding some noise to it. All right? If I didn't add this noise, then my data would have been on the line. So this is just the generation process. Now what I want to do is I want to do the training to find this line again, find this w again, right? So this is sort of a, it looks strange because we already know w, but this is just for the illustration. In reality, you would not have w. You would just be given some y and some x, right? And then you would have to find the w. But in this case, just to show how close we can get, I've done this, right? So I've added some noise. So I'm closely following what the assumption of linear regression is, right? Because linear regression also says that your y is w transpose x, which I'm doing here, plus some noise, some Gaussian noise with zero mean, and this is the variance, right? Okay, so now you can use the linear regression tool in sklearn to learn this model, right? And internally, it would be doing that x transpose x inverse and everything. The reason I'm not showing that to you is because that's what you have to do for assignment, right? So don't use this for your assignment. You won't get any points. So when you do this, this is the equation that you get. So this is the w that you get. This is the intercept part, and this is the second parameter, the second weight. Remember, in linear regression, what happens is that it automatically adds the intercept. Okay, so if you so which means that I did not explicitly add a column of ones, but when you implement it, you will have to take care of that. Anyway, so what we see here is that this does pretty well, right? Because this one was my equation that I started with, minus 3.8 and 0.11, and this is what I learned, which is fine. It was a very simple data set, right? And then you can plot this line and see how good it is. And this looks like a good fit, right, for a data like this. All right, that's good. Now we will look at some issues with linear regression. So issue number one is the impact of outliers. So what happens if my data has an outlier? For example, in this case, I have added another data point in my training data set, which is way over here. Like for this x value, the y is this. So it's clearly an outlier because it doesn't really follow the general model, right? However, when we add this, what happens with linear regression is that it gets impacted a lot. So remember, without this outlier, this is what we were learning, right? By adding one outlier, my estimate has changed a lot. So essentially what that means is that linear regression is very susceptible to outliers. The reason being that it tries to minimize the error, right? Now, if it fits a line like this, the error that it will, the penalty that it will have to pay for this point is very large, because it will compute the error, that y minus w transpose x, and it will square it. So that error becomes huge, right? So what it will try to do is change the line so that it sort of lessens the impact of this outlier, right? So if you look at that line here, this is what the line looks like, right? So earlier our line was like this, but now it has changed. Instead of going through these points, it's actually shifted a little bit to account for this point as well. But that's not what we want. However, there are ways to address this, right? So what I will do from now on is I'll discuss issues with linear regression, and then I'll show you how there are models to address those issues, right? So the first one is linear regression's susceptibility to outliers. The way to do that is to do something called robust regression, okay? So I will talk about what robust regression is, but I just want to demonstrate it. So there is a package in stats model which does robust regression. It works the same way, but what it does is that when you run it, these are the weights that you get, even with the same data which had an outlier, right? Which means that this method does not get impacted by the outlier, right? Which also kind of means that this model does not chase the data that much, or it doesn't overfit to that extent, right? An overfitting model would have, taken this into account as well, but this model does not. So when you plot the line, you see that this line completely ignores this one, as if this didn't exist at all, right? And how it does that, we'll look at it. We'll look at it now. Now, the reason linear regression is so susceptible to outliers is, as I mentioned, is because of that squared error, right? So if you look at the error, right, here, this is the primary reason that the linear regression doesn't do very well, right? Because every time if there is an outlier, the penalty that it has to pay in that error function is square of that error, all right? The same thing you can look at when you look at the probabilistic interpretation, right? In the probabilistic interpretation, again you can see there is a square over here, right? Because of this square, the likelihood goes down by a lot if there is a outlier, and that gets impacted too much, okay? So one way to address that is to come up with another distribution in which this square is not there. So if I remove this square and replace it by just a 1, right, then the impact of the outlier will be lessened, because the penalty that you would pay by introducing an outlier would not be square of this difference, but it will just be that difference itself, right? So that is the idea behind robust regression. So in robust regression, what they do is, instead of assuming that your data is normally distributed, they use a different distribution which is called, well, you can use multiple distribution. So one of them is, what they say is that yi is a Laplacian distribution. So a Laplace distribution with this, so it has similar parameters like a normal distribution, but in its, if you look at its PDF, you will see that instead of having a square here, it has an absolute value there. Because of that, it is slightly robust, or not slightly, but it is robust to outliers, okay? So Laplace, I want to see, okay? Okay, I don't have like a discussion that I wanted. All right, let's go back. Okay, so Laplacian distribution is just, I mean, conceptually it is the same idea as a Gaussian distribution, but it has a different PDF, which means that it has a different sort of the curve, right? So it has, so these are 3 different distributions that I've drawn. There's another one which is called student T distribution, which is very popular in statistics. So they all have different PDFs. What happens is, if you look at their these density curves, is that this one is Gaussian, right? If you look at Gaussian, it has a pretty long tail. It has a pretty long tail, I suppose, right? It has a long tail, right? Which means that it keeps going on for a long time before it hits sort of close to 0. However, these other distributions like Laplace, they have this sort of drop out very fast, Okay, so they are high here, but very quickly they drop out, right? Which means that the error that you pay, now this is essentially the error, right? So if you have no error, when your y is equal to w transpose x, then this is the value that you will add to your likelihood. But when you go higher, then this is the penalty that you will pay, right? So it will keep going, it will keep increasing. With Laplace, what happens is that very soon it will start becoming zero because of that absolute, which means that the impact of outliers is less, because the outliers will have impact over here, and here the value becomes zero quicker for for Laplace or student t compared to Gaussian. So this is how sort of this Gaussian distribution works, or this robust regression works, right? Any questions so far? I think in sklearn, this package I used from stats model, but I think there is one in sklearn as well. I'll try to find that. All right, so that is one issue with linear regression. Issue number 2 is, of course, the second issue is that it imposes this constraint of a linear relationship, right? Because it assumes that y and x are linearly related. But what happens if they are not, right? So what happens if your data looks like this? Right? Clearly fitting a line might not be the best answer, right? So if you apply linear regression to this, what it will learn is maybe something that looks like this. This will be the linear regression line. However, here you could see that maybe a nonlinear curve might be better, right? So, but linear regression by itself does not have the capacity to learn nonlinear curves, right? So now how do we extend linear regression to address that? So one way to do that is by introducing the notion of basis functions. So what this does is, or basis, well, we call them basis function expansion. So basis function is any mathematical function that gets applied to an argument, right? So let's say your x is just one number. So let's say your d is equal to 1. Okay, so x is in just one dimensional R1. Now, if I, instead of x, if I use x square, if I replace x by x square, right? So that is called a basis function expansion. Here we are not expanding, but what we can do is we can replace x by x to the power 1, x to the power 2, x to the power 3, some x to the power p, right? So instead of having one variable, suddenly you have p variables. Of course, they're all related, but they are all sort of capturing different aspects of x, right? So this is called, and typically we also include the bias, so sometimes we also write it like this. So this is called basis function expansion. You're expanding your x to model the nonlinear dependency, all right? But this is not the only thing that you can do. You can also say x is sine of x, comma cos of x, comma some arbitrary function of x, another function of x. So it could be anything, right? You can be creative and you come up with any function, but typically this is sort of easier to understand. So this is what we also know, this is also known as polynomial expansion, right? So what we are doing is that to give linear regression the ability to learn nonlinear curves, we are doing this basis function expansion, so that now and next time you will see how linear regression now can learn this. Okay, so let me get back to the slides. Any questions so far? All right. Yeah. So what we do is we replace x with some nonlinear functions of x, right? Typically this phi denotes those functions, right? So phi is basically a set of functions. So the effect of phi is that you are replacing x by a vector, okay, where we are applying multiple functions to it. So now your model becomes y given x is w transpose phi of x. Okay, so it's a normally distributed function around this as the mean. So the model is still linear in w, right? We are still, your w is still taking your features and combining them linearly. So we still call it linear regression, but but your x's are no longer just the standard x. They are linear non-linear function expansions of your x. Okay, so it is non-linear regression, but it is still linear in w. All right, so this is also known as basis function expansion. So next time what we will see is what this lets you do. I should have p here. That as you increase p, you can fit more and more complex curves. All right. So for example, so let's say if your p was 0, which means that you were replacing your x by a number 1, then you would only learn a horizontal line, of course, right? But as you increase p, so if you make p is 1, then you are learning a line, right? That's just your standard regression. If you put your p to 2, then you are learning a quadratic curve. As you keep increasing, you will learn more and more complex curves. All right. So this way, you can extend your linear regression to model nonlinear dependency. But the issue that brings in is that sometimes it would lead to overfitting, and that's where then we need to talk about regularization and how to control or clamp down on too complex solutions. All right. That